I am Sarah Chasins. I'm a professor of computer science at UC Berkeley. I am here today to answer your questions from the internet. This is Coding Support. TechGuy21, or it could be TextGuy21, it depends on if it's a reference to LaTeX or not, says what remnants of the early World Wide Web are left. And it turns out that the first website that was ever put up is still available to us, so I actually have it here on my laptop right now. So this is a web page put up in the early 90s by Tim Berners-Lee. It's describing what the World Wide Web is because Tim Berners-Lee is actually the person who created the World Wide Web. And we can see that it still displays in a totally readable and manageable manner in our modern web browsers, right? This is just Safari. But someone also actually recreated what it would have looked like in a browser of that time. So here we can see we've got the World Wide Web. It's all the same content, but of course it shows up very differently because the machinery they were working with at the time was working differently. The browsers they had made at the time were working differently. It's giving us instructions on how to actually browse through the rest of the page. It's all the same content, but obviously it's showing up a little bit differently. Admirable Long 9546 asks, new to coding, is it always this difficult? The easy answer, no. Every skill that you have ever learned in your life where parts of it became automatic over time, when you started riding a bike, they eventually became automatic. When you started playing guitar, it started becoming automatic. The exact same thing is going to happen with programming. No Confidence 5070, oh, I'm sorry about the username, asks, can I still learn programming if I hate math? The answer is yes, absolutely, absolutely 100%. So there are some kinds of math that make some kinds of programming easier, but it's not all kinds of math and it's not all kinds of programming. For that matter, there's some kinds of video games that give you practice with some of the things that make programming easier, right? Like there are lots of different skills out there that you might be practicing that might help you with some of the same things that you're gonna need in order to do coding tasks. Math is one of them. Again, it's not even all math. There are some types of computer programming that you might want to do that probably would demand a little math from you. So there are parts of the computer programming world where you probably want to be comfortable with some parts of math, but no, you can absolutely, absolutely, absolutely get into programming, get really good at programming without being into math. Someone on the internet asks, what were the earliest computer viruses like? How did they infect and affect computers? In about the early 70s, computers had started to be sort of connected with each other through something called the ARPANET. We didn't have the internet yet, and so you could go ahead and start spreading things that way, and there was this virus called the Creeper. It would print something out on the screen that said something like, I'm the Creeper, catch me if you can. Then they had to come up with the Reaper to go in and get rid of the Creeper program that was running on these machines. Demand 2010 asks, how did programmers code the first ever code? Early on, there was the ENIAC. And the ENIAC was sort of the first computer that we all look at by modern standards and say, yep, to us that looks like a general purpose computer. It looks a lot like sort of old school telephone switchboards where you're just plugging together wires in different parts of it. And that's actually how you're communicating what you want it to do. Eventually folks figured out how to use punch cards, stiff piece of cardstock kind of a thing, and you're punching holes in it. And that was the way that we fed instructions into computers for a long time before we started storing programs in memory. So originally the humans were just writing those ones and zeros. This was really painful. All this manual effort was really exhausting. It took months. And so this amazing thinker, Grace Hopper, developed the term compiler. Grace Hopper was this amazing early computing pioneer. She was a mathematician. She was incredible. And came up with the idea that instead of all these human people doing compilation, we should have a program on the machine that is actually going to do the compiling for us. And so that would be the compiler, and she invented this tool called A0 for putting together a bunch of different sort of portions of a program, a bunch of different sort of semi-related portions of code and getting them to talk to each other. And that was sort of the predecessor to the modern compiler. In fact, since that time, we have piled all this extra stuff on top of it so that the thing that Grace Hopper wrote in the early 50s actually no longer even looks like a compiler to us, right? It looks like one of the sort of subcomponents of a compiler because we have all this other stuff that we've built up on top of it. Better Sir 9013, what is the difference between programming languages? Why are some of them considered harder if they're all just same lines of code? There are lots of different things that can set programming languages apart. A big thing that I tend to think about is how much they sort of have your back. So a really common thing is for a programming language to be automatically trying to capture some kinds of bugs for you, trying to prevent you from running into some of the problems that might come back to bite you later. Some of them are saying, you know what, you're on your own. Like, just write what you want to write, put in whatever bugs you want to put in, I'm going to run it for you. So an example of something in that general category would be C. There are other programming languages that are saying, you know what, I'm going to try to catch at least some bugs for you. Maybe not all the bugs, but I'm gonna try to catch some bugs. And I'm gonna try not to get in your way. I'm not gonna try to demand a lot of extra information from you in order to do that. And so an example of something in that class would be maybe Python. And then you might have some other language over here that is really, really trying to have your back. It is gonna try to catch as many bugs for you as it can possibly catch. And the way that it's gonna do that is it's gonna demand extra information from you. So it's gonna make you work harder, but in exchange, it's gonna catch a lot of those bugs for you. An example of something in that general zone would be Rust. Faints High asks, working as a programmer, what do you actually do all day at work? Unfortunately, the answer is not as much programming as you might desire. In general, a lot of programmers get into programming because they like programming. And then it turns out that a lot of what they're spending their day-to-day on is talking with other programmers about how to get this person's piece of code to talk with this person's piece of code, how to make all of this sort of big code base work together, or you're talking to the client or the customer or someone who's gonna be using this piece of code and you're figuring out what their needs are. You're having a bunch of meetings in order to figure out what the program should actually do. And then you're squeezing in as much of that actual code time as you can, because that's usually the fun part. DG Holmes asks, is Python really the second best language for everything? I think probably whoever said this first, honestly, they were probably trying to get a dig in on Python a little bit, kind of trying to say that it's not the first best language for anything. But the other way of reading this is to say that Python is very flexible, and it's true, Python is incredibly flexible. There's all kinds of programs that you could comfortably go and write them down in Python. You're probably gonna have a good time. I have a personal fondness for Python, and I have no bad feelings towards Python, so thumbs up, learn Python. A Reddit user asks, is it worth learning C++ in 2025? The easy answer to this is absolutely. The follow-on answer is, if you're entering an existing code base and it's already written in C++, okay, great, it's already written in C++, you're gonna probably use C++. On the other hand, if you are starting a new project, see if you could use Rust. Just take a look. Roy Rust Dev says, why is Rust the most loved programming language in Stack Overflow surveys? Why do you love Rust? Do you try to convince others to learn Rust? Rust is probably one of the most exciting newish programming languages that we have available right now. They have been incredibly thoughtful about so many different parts of the design of this language. One of the things that people are really excited about is just they've been thoughtful about the error messages that you get when you do something wrong. Honestly, that does actually matter a lot when you're getting up and running with a language. But if you look even more deeply into the design of the language itself, it is bringing together sort of the best ideas from the past 20 years of new research in programming languages land. So there have been all of these really exciting ideas about how we can help programmers catch more bugs. This idea of the programming language should have your back. It should be looking out for the things that you might do wrong, and it should be catching those in advance. Rust is doing that at a level that the other languages out there kind of aren't really doing, while also being just incredibly fast. So if you are thinking about, oh, I'm gonna have to use C in order to write this, in order to make sure that it's fast enough to run, you might also be thinking about Rust at this point, because it's high performance, but it's also, again, it's got your back. Star Knight 12 says JavaScript is a goated language. I don't know why people hate it for no reason. I get what you're saying. I think in general there are some reasons to be a little bit skeptical of some of JavaScript's design choices, but basically, if you're feeling dissatisfied with JavaScript, just learn TypeScript, right? If you're trying to write something out on the web and you're so frustrated at being locked into JavaScript, no problem, learn TypeScript, you're gonna be happy. This is a very exciting one. Brilliant Sir 5729 asks, how on earth do programming languages get made? Someone has the idea for, I would like to write out this kind of program. I want the program text to say this, and here's what I want it to do. And then all of those steps that it takes in order to convert something in that high level representation all the way down to the ones and zeros, you are now in charge of that. The process of doing that is called writing a compiler, or you might instead write an interpreter. There are multiple different ways of implementing a programming language, but basically, yeah, what it takes is an idea. So you don't necessarily have to generate assembly instructions, because it turns out we have all of these existing programming languages. And so you can take advantage of that in order to implement your new language in a way that's maybe easier for you. So maybe I want to invent Unicorn Lang, right? I can go ahead and write my compiler that compiles from Unicorn Lang to Rust, which is an existing programming language. Now that I have this Rust program coming out the other end, I can then feed that into the existing Rust compiler and use that to actually get all the way down to the ones and zeros. So you can start stacking together these different compilers. Cheap Long Steak says, why do computers just use the binary code zeros and ones? When we're writing numbers in our day-to-day life, we are using base 10. We have the digits 0 through 9. Whereas for computers, as we've talked about a bit, we are using zeros and 1, base 2. This is not necessarily innate. This is not enforced. The very first computer that we all sort of recognize as a computer, the ENIAC, actually used base 10. It can be done. You can totally do it. Remember that the way that we're representing this information inside the computer is by how much electricity is flowing through a part of the computer. And so go ahead and imagine I have put you in a room, there's a light bulb in the room, on the other side of the wall, I'm controlling a dimmer switch. I want you to tell me if we're at the low position of the dimmer switch or the high position of the dimmer switch. And I'm gonna sort of mess around with that outside, and every time I yell out to you, you have to tell me low or high. If I'm just giving you low and high, you're probably gonna be able to do that pretty reliably. I can be a little bit off in how much I've messed with the dimmer switch, and you're probably still gonna be able to shout out low or high. Now, instead, say, I've picked these 10 spots on the dimmer switch, and I want you to be able to yell out 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 based on where I've put it in there. But remember, you're in the other room. You're not seeing what I've actually done on the dimmer switch. You're just seeing the light bulb. So say I stick it to 5. Some of the time you're probably yelling out 5. Some of the time you're probably yelling out 6. Some of the time you're probably yelling out 4. It can be done to use base 10 inside the computer, but if you think about sort of, okay, we're trying to figure out how much electricity is flowing through this, it's a lot easier. It's gonna be a lot more reliable if you just do the 1s and 0s. Illustrious Run 4733 is asking, why is debugging harder than writing code? It is so much harder. Basically, the answer comes down to your mental model of what the program is doing versus what the program is doing. If you're going through the process of writing something up, right, doing the original draft of your program, you're not even necessarily at the point of testing if your mental model is aligned with the program. But basically, our sort of view of what's happening this entire time is, okay, this is what I'm expecting the program to do. You are keeping your mental model well aligned with what the program is doing, and so you're sort of building up the program bit by bit, continuing to make sure throughout that it is doing what you expect. If we hit the point where we are doing debugging, where we're trying to find something that has gone wrong, then our mental model and what the program is actually doing have diverged. Even harder if it's something that you didn't write, because then you're having to build up the mental model from scratch. You don't have any mental model in there to even start from, so you're having to go through and do that sort of difficult process of reading code, figure out, okay, what am I expecting this program to even do? Pleasant Relation 144 asks, how do you guys remember all the syntax? We don't necessarily. It turns out, you know, in contrast to, say, I am learning Spanish, right? I'm gonna go and I'm gonna be trying to speak to someone in Spanish. I'm not trying to be looking at my computer every time to translate a word. In contrast, if I am at the editor and I'm typing out my code, I've got the computer right there. If I've forgotten something, I can just look it up and it's no big deal. Red Pajamas asks, how do I know if I should learn backend, frontend, or full stack? The answer is you probably don't know in advance. You really probably just want to try it. So it could take a few years to be really, really comfortable and feeling really like an expert in any of these spaces. But to get a sense of what the day-to-day would look like, to just try it out, in a week or two, you can probably have a pretty good idea of what these programs look like and if you enjoy writing them. Kavinda14 asks, how can computer scientists contribute to CRISPR? So I absolutely love this question because I'm really excited about work that does bring, I specifically think about programming languages work, but also computer science more broadly into conversation with other disciplines. I think that's really powerful and really exciting, and more folks should be thinking about it. But I think the actual answer here is go out and talk to the people who are doing the work you want to support. So one of the pieces of advice that I give my PhD students all the time, and they're amazing at doing this, is they will just go out and become apprentices to the teams that are doing the kind of work that they want to be supporting. So for example, I have an amazing PhD student who is currently basically embedded in a biology lab. You know, he's a computer scientist, but he's learned how to pipette. He's taken biology classes. He's in their labs helping with programming tasks. He is there doing the work of understanding their day-to-day. Because unfortunately, it's not quite as simple as, okay, we can just get everyone sort of from the bio side to type up 1 or 2 paragraphs about their problems and off we go. It takes work to figure out what are the real gaps there and what are the things we could do to fill it. So go spend time with the audiences, the communities that you are excited to serve. I think it's really powerful. Senior Pineapple, or perhaps Senor Pineapple, asks, how hard would it be to build my own game engine from scratch? And the answer is very hard. You will probably also have a really fun time though. In general, a big thing that you're gonna spend your time doing is deciding what abstractions you want your programmers to have access to. Basically, an idea or a word that they can use repeatedly. If you have a pre-built snippet of code that is gonna do one big long thing, but they get to call it by just a short name and reuse that code over and over again. And so what you're doing when you build your own game engine is trying to anticipate what are those snippets of code that people are gonna need to reuse and reuse and reuse? But it turns out for building a real game, right? For building, especially if you're thinking about maybe a 3D game, it's gonna be a lot of different things that the programmer is gonna need to do, and it is gonna take you some time to get there. The other thing is that there are certain parts of, depending on how low level you're deciding to go, like maybe you're building this on top of an existing game engine, in which case maybe you're not gonna have to deal with this. But if you are going all the way down to deciding how every pixel is gonna appear yourself, you're gonna end up doing a lot of computer graphics type of computation, which involves some amount of math. So this process is super, super fun, And if you are interested in game programming, writing your own game engine is a very interesting exercise, but is definitely not gonna be the fastest route to a game. Martholomew asks, is ChatGPT really as revolutionary as it seems? Compared to other tech breakthroughs, I say not so much. I think it comes down to whether you are personally interested in tasks where the goal is to put together words that look good together. If that is gonna revolutionize your world, fantastic. ChatGPT is built on a kind of program called a large language model. A large language model is basically a program for putting together words that look good together. And so the approach that large language models designers actually took was, okay, what we're gonna do is we're gonna go out and collect all of the documents we can find on the web, all the web pages themselves, all the other documents we can rustle up. And these are basically, words that humans have put together. And so we have some pretty good evidence that humans think these words look good together. And so we're gonna make it play the fill in the blank game on these documents. I might have a simple document. It says, the dog has 4 legs, right? So I'm gonna go ahead and feed that to the program, and I'm gonna say, blank dog has 4 legs. The first time it answers, it says sky. You say, no, you silly program, not sky, the word is the. That's the word I want in there. You go again, you fill in the second word with a blank instead. So it's the blank has 4 legs, and it says swimming. You say, no, you silly machine, not swimming, I want a dog there. So you repeat this process for about 300, 400 years of compute time, because you can split up the work across a bunch of different computers and then get them together to sort of mash together their cheat sheets at the end. We've already sort of shown it the answer, and you might say, Sarah, this doesn't seem okay. The program is going to be able to cheat. That is exactly the point, right? You are trying to get it to cheat. You want it to cheat. And so you are going ahead and you're giving this LLM, this large language model, a cheat sheet. And if you've ever heard something about sort of the number of parameters that a particular LLM has, that is about sort of the size of the cheat sheet that it was given. You make it play the fill in the blank game for about 300, 400 years of compute time. And then at the end of that, you have a program that is pretty good at fill in the blank. Now, this does not automatically give you ChatGPT, but it is pretty easy to turn one of these into a chatbot, right? Because now we just make a new document and it says something like, this is the transcript of a conversation between a human and a chatbot. And then the next part of the document says, the human has said, what is the capital of Sweden? The chatbot has said, blank. And so it now fills in the blank because it's good at playing the fill in the blank game. And so maybe it says the, and then you go again, but now it says, the chatbot says, the blank. And maybe now the next word it comes up with is capital. And you just keep going through that process, And so that is what is going on with large language models. It's just programs for putting together words that look good together. GPT Girl Next Door is asking, with AI advancing so fast, is it still worth learning to code deeply? Yes, you still need to be able to write code the old-fashioned way, for the most part, in order to get programs out from these generative AI tools. So the first thing is that a really big skill that you learn over the course of a programming education is how to decompose programming problems, right? You're starting from this big, amorphous, sort of not super well specified, large problem, and you're figuring out, okay, well, I can break it into these 2 chunks, and then I can break that chunk into an even smaller chunk, and you keep doing this all the way down to something really small, small enough that you can actually answer it with a single line of code or a couple lines of code. If you haven't been trained to do that, it's not necessarily particularly easy to do. And so if you're just giving sort of these big, vague, open-ended things, it's really hard to turn that into a useful program that's actually going to work and run. The next big thing that comes up is the kinds of human language text, for example, English text, that I would write if I'm a non-programmer usually look different from what I would write if I was a programmer. Over the course of all the documents that got fed into the large language model in order to figure out what words look good together, the documents that had code in them were usually written by programmers. And so those were using the sort of programmer-style human language descriptions next to the code. And so even if the human language descriptions that a programmer would write might produce good code, the other alternative ways of describing those problems might not work. In order to use these tools, these generative AI tools, in order to actually generate useful programs, you mostly have to already know how to write programs the old-fashioned way, which is frustrating for a lot of folks, but that seems to be the reality, at least right now. Minute Order 4809 asks, what is the best way of using AI while coding? My first answer would be, are you sure you have to? Double check. But if you've decided, yeah, I'm going for it, the thing you want to do is first break down your problem, whatever sort of shape that problem has into the smallest portion of that problem that you can think of. Ideally, this should be something that's going to be about maybe 5-ish lines of code, something like that. And then instead of writing it out in sort of standard human language, write it out in pseudocode. So pseudocode is basically where you're describing, this is exactly the thing that the computer is going to do, and then this is the thing the computer is going to do, and then this is the thing the computer is going to do. And it basically looks like writing in a programming language, except you're just not fussed about syntax. You're not worried about if you're missing a semicolon or if the indentation is right, that kind of thing. Go ahead and feed that into your AI tool, and then you have to have a concrete plan for how you're going to persuade yourself that what comes out the other side is right. Do you have, 20 tests that you're going to run? Do you have a friend who can look at this code and make sure that it's actually doing the right thing? Or if you are yourself a programmer, are you going to go through and make sure that it's actually doing the right thing? So have a concrete plan for how you're going to check it, or just don't use it. Add Historical 6271 is asking experienced developers, what has your experience been with vibe coding? Vibe coding is when we use one of those large language models or something like ChatGPT or one of the other tools built on top of that same underlying generative AI technology to generate a program instead of writing it out the old-fashioned way by just typing a program in our programming language. Vibe coding seems to work okay if you are rewriting something that has already been written many, many, many times before. On the other hand, if you're trying to do anything new, it's probably not going to get you anywhere. The best bet really is to carve the problem up into teeny tiny chunks and then sort of use your own reasoning to actually do the programming. There's been some really interesting studies about this that looked at sort of the differences between whether it actually makes someone more productive versus whether they perceive that it makes them more productive. It turns out using an LLM-backed tool made them 20% slower. But even after doing the task with the tool, they all said they thought it had made them 20% faster. Ulterior Kid 324 asks, what does live coding actually look like? So basically, anytime that you are programming, you're probably doing it live. I don't really know what the alternative is, so you're probably doing it live. But usually we use this term specifically when we were talking about doing it in front of an audience like y'all. So I'm gonna go ahead and do that right now. And we're basically gonna use this as an opportunity to see what are some things you can do with honestly a pretty short, pretty simple program, but we're just gonna talk it through step by step. So I'm now gonna pull up an editor. We've got this tiny little program in here. So we have this URL, sort of an interestingly structured URL, but it's the same kind of URL that you might type into a browser. And then we have some country codes, and this one has a lot of them. But then here we have sort of a smaller list. We can see USA, Mexico, Canada. Let's start by just printing this out. So let's go ahead and print fewer country codes, and programmers love to start counting at 0 instead of 1, but that is in fact referring to the first item in the list. And we will copy that a couple of times because we're gonna wanna print all of the items. This is called TinyMap, so I will run TinyMap. You can see it has printed out those country codes. It's not an exciting program, but maybe I want to actually use those strings, those little pieces of text, in order to modify that original URL. So instead of just having the country code, let's instead copy this where it says USA in the sample URL. I'm going to go ahead and replace that with the country code that we are trying to use. Let's go ahead and pop that in there. We want to start with 0. And again, we're going to have to do the thing of copying and pasting a couple of times. Here we go, Python 3. We are now seeing our variants of the URL. We can see we've got the one that has USA. We've got the one that has Mexico. We've got the one that has Canada. But we probably aren't that interested in just printing out a URL. We're probably trying to actually do something interesting with that URL, like maybe get some data back from it the same way we would if we popped it into a browser. So let's go ahead and open something called a library. Basically, if some other programmer has made a bunch of little program snippets and they said to themselves, this is going to be useful for a lot of different people, I'm going to make it available, we would call that a library. So I'm going to go ahead and import requests. So instead of print, let's now have requests.get, and we will go ahead and repeat that process for all of these URLs. I'm starting at this point, personally, to get pretty bored of just retyping out this same big long string every single time. I'm starting to think maybe there's something that could help me avoid doing all that copying, pasting, maybe sort of automate for me the process of doing some of this. Let's get introduced to a loop. A loop is going to let us do something repeatedly for a bunch of different items that have some similar structure or for which we want to do the same kind of thing. So for I in range length of fewer country codes, let's go ahead and do something. Let's probably go ahead and do that requests, but I don't always want to do it for the first item in our country codes list. I'm probably going to want to do it for the ith item, right? The 0th, then the first, then the third. Right now, we're not having anything printed out, but I'm going to show that this is in fact going to run it for everything. So I know that request is going to give me back some JSON. JSON is just one of those standard formats that we have that lets us represent data in a way that lots of different programs can understand. So if you have a standardized way, then your different programs can talk to each other. So let's go ahead and print out the JSON that we're getting back by running each of those requests. Okay. Big, messy JSON, not super fun to read. Let's add ourselves a couple little sort of separators just to make it a little bit easier. We can run it again. Okay, we are now seeing these are split apart according to which of the 3 items they were associated with. I'm looking for this life expectancy data, and I know that this sort of particular part of the URL is that. And I know that the particular part that is going to tell me in this JSON what we're actually going to have as the value is this numeric value thing right here. So I'm going to go ahead and pop that into the code so that I don't have to just look through all of this. Let's give this a name. What shall we call this? We'll call this just the JSON. And then we can go ahead and get out from the JSON whatever is the portion that we are looking for. So JSON, I think this is inside the value. And we only want to get one item, this numeric value. So let's call that something. Let's maybe call that life expectancy. So now I want to go ahead and print out country code, this value right here. And we just have to make sure that we have stored it, we've saved it, we've given it that name before we actually use it. Let's print out both the country code and the life expectancy, and let's see if we're getting the data that we're expecting. Looks good. We can see the life expectancy for these 3 countries that we were looking at. Okay, let's go ahead and actually save that data because maybe we want to do something else with it later. So let's make a new list. This one will be empty, and we're going to go ahead and fill it with the data that we're grabbing from these calls to the requests library, from going out to the web and saying, bring me back the data for this country. Let's keep on printing it too. Let's also go ahead and add it into data. So we will append to the data list, and we will go ahead and put in country code and life expectancy. Let's print out our data at the end of the process just to make sure that this is actually looking like we're expecting it to look. I'll run the program again. Okay, we are seeing that data at the end. What if we put it on a map? Again, we're going to want to use a nice library that someone has built for us. So let's import plotly.express, and we'll call that px. So now, instead of just printing the data, let's also make a figure that represents the data. So fig equals px dot, I think it's chloropleth, and let's use our data. And now we're going to have to tell it what are the locations and what are the things that we want to visualize in this. So I'm going to say locations, and I'm going to have that be 0, meaning it's the 0th item in each of these pairs. We can see that right here. We can see country code is on the left, so it's the 0th item, and then life expectancy is the 1th item, or in the sort of more usual terminology that you and I would use day to day, it's the 2nd item. So let's go ahead and say colored equals 1. And once we have actually got that, let's actually show the figure. So here we go. We've got our program ready to go. Fantastic, we can see our little map. Here it is, it's got those 3 countries colored. We probably are interested in doing it for all the countries, so I'm just real quick gonna go in here and actually change which of these lists we're using. So you can see that we've just been using these fewer country codes, which just says the 3, but why not run it for all the countries, right? The data's there, so let's go ahead and use some country codes instead of fewer country codes, and let's get rid of all these old unnecessary lines, and then we will have our final program. So here we go. It is going to talk to the internet. It's going to collect the information for all those different countries. And after a few moments there, I think it was a little under a minute, we've got our map. It's got the data for a bunch of different countries. HGMIV926 asks, how do I read code? This is honestly an incredibly difficult question to answer because reading code is actually really hard. It's not like when we're sitting down to a piece of text. We're going to start on page 1, we're going to go to page 2, we're moving in this sort of linear manner. That's not how we typically do it when we're reading code. Don't take this advice if there's any chance that your code might be malicious. But if this code is not malicious, go ahead and run it. Take a look at a part of the output that you are interested in, you want to follow up on. Go figure out what part of that code actually created that output, and then start working your way back, right? What were the outputs that came out of some earlier part of the code that ended up going into the process of making that output? There are even debuggers that are specially built to sort of help you work through individual executions of code. So one of my favorite kinds of debuggers that I really like is called time travel debugging. You've gone ahead, you've done an execution of your program that you're interested in, but maybe you actually want to walk it back. You want to travel back into the past to see what was happening before. You can go ahead and do that. If you then want to travel ahead, you can do that, thus time travel. Vedro 3 asks, how do computers understand code? I'm gonna talk us through it with a specific concrete program. I'm gonna show us how we get from something that looks kind of like a computer program that you might have seen places, all the way down to the ones and zeros that you can then actually store in the machine. And we'll draw the 4 stages that we take it through. So this is gonna be, just the input to this entire process. So here we go, we've got 1 plus 2 plus 4. Now, the very first thing that needs to happen is I have to figure out which portions of this to treat separately versus together. I'm gonna just do that by underlining. So the left parenthesis is gonna be on its own, the 1 is gonna be on its own, the plus sign, the 2, the right parenthesis, the plus, the 4. You can see we've ignored these spaces. We've got our left parenthesis, our 1, our plus, our 2, our right parenthesis, our next plus, and our 4. This stage, what I've just drawn out, that is called lexing or tokenizing, because the things that you see in this list on the right are the tokens. So the next thing we're gonna wanna do is turn this into something that we can actually sort of use to understand something about the structure of this program. So here at the root of something that I'm going to call a tree, we're going to have the addition operator. And this is going to be the operation that's going to actually happen second, because what we want to do is we want to make sure that that 1 and that 2 that we're adding together, we can see that those are in parens. We actually want to do that first, right? Because that has been grouped. We'll have a 1 on the left and a 2 on the right. And then what we have on that last branch there of the top add is going to be that 4. Now we can start to see that there's some structure happening here. We can see that sort of the 1 and the 2 are going to be grouped together by some operation, and then whatever we get out from that operation, that's going to be grouped together with the 4. But actually, a lot of folks know that what goes into the computer eventually has to be 1s and 0s, and there's no clear way necessarily at this point to turn this into 1s and 0s. So now we're going to turn it into something called instructions. And instructions are basically just going to be the things that the processor knows how to handle. So here we go. We're going to go ahead and write out move 1, right, because that's the first value that we're dealing with, into R8, one of the slots that the computer has available, and then maybe we will move into R9, another slot, the value 2. We now have everything we need to do in order to run our first addition. So let's go ahead and do an add instruction, and we'll go ahead and add together what we've got from R8 and R9, and that is going to put that value inside R8. So now let's go ahead and move that 4 into one of these. So we're no longer using R9 anymore for the thing we were previously using. So let's go ahead and move into R9 the value 4. And now if we do add R8, R9, we should get the result of the entire program in there. And then this phase, where we're actually taking that nice structured representation of the program and turning it into instructions, that is actually called code generation. But at some point, it actually has to turn into 1s and 0s. So let me go ahead and highlight some common structure that we're seeing across these instructions. We can see that there's sort of this thing, and then there's this thing, and then there's this thing. And it turns out that we have a scheme for turning each of these into a binary number. And then we do the exact same process for all of those instructions. And finally, what we have is just 1s and 0s. So now I'm going to turn to the computer. All right. So here we are in something called x86-64 Playground. This is just a website. You can visit this on your browser. I have typed in the instructions that I was drawing over here on the iPad, and so we're now going to get to see what it actually does to a representation of the computer's state when we are running through these instructions. So here we go. We start with that first move instruction. You can see that over here in R8, we now have the value 1. So let's go ahead and run the next step. Fantastic. We can see that now inside R9, we've got that 2 value. If we keep going, we're now going to see that we've done the addition, and the output from that addition, the value 3, that now lives inside R8. Fantastic. One more. We've got moving the 4 into R9. It's okay for us to reuse R9, right? We're not overwriting anything that we're going to need later, so it's totally fine. We can go ahead and get that value into R9. And then one more, and we can see that we've done that last addition, and we've got the final output 7 represented inside R8. And that is how the computer understands the code that you write. That's it. We have run out of questions today. I hope you all have learned something new. I hope you're excited about programming languages and maybe even about compilers. Until next time.